In this video we'll look at how we do some sort of optimal bias so that you can get the maximum swing at the output. So most circuits are used with passive devices, so you don't really AC couple them to ground. I just wanted to show you that the device is capable of giving a larger gain. You usually like the gain to be controlled by some controllable passive devices and not by some bias region of the transistor. So my full range is 10 volts, and I will always have 1/10 of the voltage I need to give for this 100 ohms as I'm giving for this 1 kilo ohm. So I'm assuming that the load is 1 kilo ohm and it's fixed. So if I look at my full budget, I have 10 volts. I have a gain of around 10, so my output needs a much larger swing than my input. In addition to that, I need a small voltage across the transistor for the transistor to work, and this we haven't talked about. So right now let's say I'm going to give half a volt for that. If the voltage I give here is V, then this is, well, it's 9 times V, but let's say it's around 10 times V. Okay, so we're just designing for some margin. So 11V plus 0.5 should be around 10 volts. So that's 9.5 by 11 is the value I can give for voltage. So 9.5 by 10, that's around 0.9, 0.95, and then 10% less than that, so another 0.9 less than that, so around 0.86. So 0.86 volt is what I can afford when I get the entire, I give most of it. So if it's 0.86, then into 1k, so 8.6 volts I'm going to give to this guy, and then I have some 0.5 volts that I'm going to give for the other guy, for the transistor itself, and the rest of the 0.86, 0.8 or whatever I give to the rest. Does that make sense? 0.6 plus 0.5, 0.11 plus 0.8, okay, in the ballpark. So we have around 10 volts for that. And if this is 8.6, then I want to sort of split it in the middle so I can swing both on top and bottom. So 4.3. So that basically tells me that the bias has to be at 4.3 volts. This is higher, this is lower. So I'm going to bias it at 4.3 volts. So that's what the center line is going to be, and above that it can go 4.3, and below that it can go 4.3, and here I'll be setting it up at 0.43, and then it can go up well, in this case it will go down as this increases. Yes, the current decreases, it goes up. Yes, that's right. So this will be the opposite. So when this is high, actually this is low, so you do need to account for the margin here also. So now if I want this to have 0.43, a 4.3 milliamps, sorry, not there, 4.3 milliamps, and this voltage is 0.43, then 0.43 plus 0.6, so I need this to be around 1 volt. So if I had 10 volts, I need this to be around 1 kilo ohm, and that to be around 9 kilo ohms, and the accurate value of that, of course, we'll figure out by simulations. So let's do that. 1 kilo ohm, 9 kilo ohm, And when we run the simulation, what we are looking for first is the bias voltage here, the signal also. So let's delete that and rerun the sim. Okay, so this is around 300 millivolts. We wanted around 400 millivolts, so we need to bump this up a little bit. Okay, and then the output voltage is, we had expected a little more, so we can bump it up a little more maybe. Okay, and now let's connect the signal back and look at what should be the signal we should feed it. The output, I'm expecting it to be 4 volts, so this can be up to 0.4 volts. So let's run the sim, and we can split it across the two windows. And by and large, you see it's a 180-degree out of phase, so this is not introducing too much of phase difference, and it looks fairly clean. We can check the gain. So that should be around 0.8, a little less than that maybe because of the capacitor. Yeah, okay. And if I switch to the other one, I get the gain of 10, so it's around the gain of 10. Yeah, 9, 10. So this way I can get a fairly large output swing, and sort of optimally bias by budgeting for it.